So before we wind up the session on Fourier transformation, let us look at some of the properties of the Fourier transformations. So let us assume that we have got a signal x of t, which is a non-periodic signal, aperiodic signal, and that's why we have selected the Fourier transformation for its frequency response analysis. Now, as we know that the signal x of t and its Fourier transform x of e to the power j omega is being represented by this particular equation. That means x of t is equal to 1 upon 2 pi integration over minus infinity to plus infinity x of e to the power j omega e to the power j omega t d omega. That is basically the reconstruction of the actual signal, actual aperiodic signal x of t from its frequency components x of e to the power j omega. And notationally, we can represent this by virtue of this particular thing. X of t Fourier transformation will give us x of e to the power j omega, and if we perform the inverse Fourier transformation, then it will give us x of t back. Now, what happens if we differentiate the signal x of t in the time domain? Now, this is the equation that we have already. X of t is equal to 1 upon 2 pi integration over minus infinity to plus infinity x of e to the power j omega e to the power j omega t d omega. Now, if I differentiate the actual signal x of t, derivative of xt differentiating with respect to time, both sides of this equation, what we get is in this side we have derivative of xt, that is equal to 1 upon 2 pi integration over minus to plus infinity x of e to the power j omega, and this e to the power j omega t is a function of time. So if you differentiate this with respect to time, we will be getting j omega outside back, j omega e to the power j omega t d omega. So now if you compare this equation with the previous equation, what we get is this ddt of xt is another signal, time domain signal, that can be represented as 1 upon 2 pi integration over minus infinity to plus infinity something which is a function of frequency. That means j omega x e to the power j omega multiplied with e to the power j omega t d omega. So that means if you differentiate the signal with respect to time, then the differentiated signal is having a Fourier transformation that is given by j omega x e to the power j omega. So what does it mean actually? So that is a mathematical representation. That means if x of t forms a Fourier transform pair with x of e to the power j omega, then ddt of xt, that means the differentiated version of x of t, will form a Fourier transform pair with j omega x of e to the power j omega. So what is the physical significance? We have to understand what is the physical significance behind this. Now suppose x of t is an aperiodic signal and it is having its variation. So suppose there is a range for the signal. Suppose signal varies from say t1 to t2. Within that particular time interval, the signal varies, and within this particular domain, let us assume that over a particular span of time, this x of t is constant. Now if this x of t is constant, then ddt of x of t will give us zero value, because differentiating this with respect to time, and if over a particular interval the signal is constant and there is no variation, so that will give us zero, right? Now derivative of xt is equal to 0 where the signal is constant. That means signal doesn't vary with respect to the time. So what is the corresponding significance over here in the Fourier domain? In the Fourier domain, we get that since the signal is constant in time, so there is no frequency variation. There is no frequency variation. It's a kind of DC signal. There is no frequency variation. That means over here, this omega component will be equal to 0 then. That means if I consider derivative of xt is my actual signal in the time domain, and if we perform the Fourier transformation in time, I mean, if we perform the differentiation in time, then the corresponding Fourier transformation will give us this j omega x of e to the power j omega. In other words, we can say that the differentiated version of the signal, that means ddt of xt, will form a Fourier transform pair with j omega x of e to the power j omega. So this is a that particular thing is a function of frequency as well. Now what happens if we differentiate the signal in the frequency domain? That means we have x of e to the power j omega, that is the component of the signal x of t, along the j omega axis. That means x of e to the power j omega. So we know the forward Fourier transformation equation, that is equal to minus to plus infinity x of t integration over this one e to the power minus j omega t dt, and we write this one x of t and x of e to the power j omega, they form a Fourier transform pair. And now if we differentiate this x of e to the power j omega with respect to frequency omega, then we find that this minus jt that is coming outside, if we differentiate this with respect to uh, omega, then obviously minus jt is coming outside. Then you have like minus to plus infinity minus jt xt e to the power minus j omega t. Now if you compare this equation with that equation, this fourth equation with third equation, we'll see that this time this entire thing, this minus jtxt, can be considered as a composite signal, and it forms the I mean this dd omega x e to the power j omega, this is a function of frequency, and this minus jtxt is a function of time, and we have this particular notation over there. So if we compare this equation with the last equation, third equation, the fourth equation, we find that minus jtxt will form a Fourier transform pair with dd omega of x e to the power j omega. So these are the two observations that we can make. We can differentiate the signal in the time domain, and if we differentiate the signal in the time domain, and if you know the Fourier transform of the signal x of t uh, uh, in the frequency domain, like x of e to the power j omega, and you are asked to find out the Fourier transformation of its differentiated version, we can directly find out this one by multiplying this x of e to the power j omega with the j omega component only. By multiplying this with the j omega component, we can easily find out the corresponding Fourier transformation. And the most important thing over here is that if I consider this particular signal dt of xt, it contains zero frequency component over there, where this is a constant. If this is constant, if x of t is constant, then dt of xt will give us zero, and then the zero frequency component will be present over there. So if you put omega is equal to 0, then it will be validated, right? So that is the differentiation in time and differentiation in frequency. Now moving on, if I consider the next property, the next property is the time shifting property. We have the signal x of t that forms a Fourier transform pair with x e to the power j omega. And if we shift the signal by some amount, say we shift the signal by some amount t naught, then what is the relationship between the shifted version and the original version in the frequency domain? So we call the new signal as y of t, that is equal to x of t minus t0, and then y of e to the power j omega can be represented as integration over minus to plus infinity yt e to the power minus j omega t dt, that is equal to minus to plus infinity x of t minus t naught e to the power minus j omega t dt. We just replace yt by x of t minus t naught. Now we do the substitution. Tau is equal to t minus t naught, so d tau is equal to dt. Tau t naught is equal to constant. We get like integration over minus to plus infinity x of tau e to the power minus j omega tau plus t naught d tau. Over here, this e to the power minus j omega t naught is independent of tau, so we can take it outside, and rest part is left over there, minus to plus infinity x of tau e to the power minus j omega tau d tau, that is equal to e to the power minus j omega t naught x of e to the power j omega. So if we shift the signal in the time domain by some amount, then the shifted version will be having a Fourier transformation, which is, as far as the magnitude is concerned, this is same as the original signal. So if you see, we have got a signal x of t, and if you shift the signal in the time domain by some amount, then the Fourier spectrum, if you consider the magnitude spectrum, the spectrum remains the same, because as you know, this x of e to the power j omega or y of e to the power j omega, these are in general complex numbers, so they have their magnitude part as well as their phase part. So as far as the magnitude part is concerned, this y of e to the power j omega and x of e to the power j omega, they share the same magnitude part, because this e to the power mod of e to the power minus j omega t naught will give you a unity value. So as far as the magnitude is concerned, we find that there will be no change, but there will be a phase difference by an amount equal to minus omega t naught, where t naught is the amount of shift being applied. So we call that x of t minus t naught will form a Fourier transform pair with e to the power minus j omega t naught x e to the power j omega if xt forms a Fourier transform pair with x of e to the power j omega. So that is known as the time shifting property. So if you shift the signal in the time domain, then essentially there is no change of its Fourier transformation, or there is no change in its frequency spectrum. Then we consider the frequency shift property. We know that xt and x e to the power j omega, they form a Fourier transform pair, and this y to the power j omega is the shifted version of this x e to the power j omega, and over here the frequency shifting is given by gamma. So we have got the spectrum x e to the power j omega. We shift the signal, the frequency transformation, frequency response by some amount gamma. Then the modified version will be to the power j omega minus gamma. Then how to get this yt? This is nothing but the inverse Fourier transformation of y to the power j omega. So if you just substitute the value 1 upon 2 pi integration of minus infinity to plus infinity y to the power j omega e to the power j omega t d omega, and if you substitute the value for y to the power j omega, that will give us x e to the power j omega minus gamma into e to the power j omega t d omega, and we do the substitution, that is eta is equal to omega minus gamma, that means d eta is equal to d omega, and over here you see there that this e to the power j gamma t, because over here omega minus gamma is equal to eta, so accordingly we can represent this omega as eta plus gamma. Then this e to the power j gamma t is independent of eta, so we can take it outside, and then e to the power j gamma t is coming outside. What we have 1 upon 2 pi integration of minus infinity to plus infinity x e to the power j eta e to the power j eta t d eta. This is nothing but the inverse Fourier transformation of x e to the power j eta, that means x of t. So if we shift the frequency by some amount, I mean the frequency of the Fourier transformation by some amount, so the result is nothing but multiplying the actual signal x of t by some complex rotating phasor e to the power j gamma t. So we shift the signal by some amount in the frequency domain. So we have got our spectrum, and if we shift the spectrum by some amount, and if you follow the notion of Fourier transformation that we have discussed during our initial lectures, that how the corresponding equations of these Fourier transformations and inverse Fourier transformations are evolving from the notion of the vector space representation, and the Fourier coefficients, this x e to the power j omega, these are basically the components of the signal along the different frequency values. Then you can easily relate that if we simply shift the spectrum by some amount, then this is essentially nothing but multiplying the actual signal x of t with some complex rotating phasor, and this has been represented over there. Now let's move to the another property, which is known as the scaling property. I've already seen the scaling operation in the signal manipulation in the very first unit over there. Suppose we have got a signal x of t, and we from the signal x of t we scale the signal in the time domain, and the scaled signal is represented by y of t is equal to x of at, where if a is greater than 1, this is basically the compression, we compress the signal, and if a is less than 1, this is known as expansion. So if I know the if I know this x of t and x of e to the power j omega, they form a Fourier transform pair, and if we just simply compress the signal or expand the signal, do we need to calculate the Fourier transformation again, or do you have any other mechanism or property by virtue of that we can get back the spectrum of the scaled version? So that can be verified over here. Y to the power j omega is given by integration over minus to plus infinity y t to the power minus j omega t dt, and that is equal to x of at to the power minus j omega t dt. So this can be represented like, if I represent at as tau, then d tau is equal to a dt, and then we have like 1 upon a integration of minus infinity to plus infinity x of tau e to the power minus j omega upon a tau d tau if a is greater than 0, and if a is less than 0, if a is less than 0, the second equation is for a less than 0. In that case, it will be from minus, instead of plus to minus infinity, you have minus to plus infinity. Same thing, either you have minus to plus infinity, or you have plus to minus infinity x of tau e to the power minus j omega by a tau d tau. So the first equation is for a greater than 0, second equation is for a less than 0, right? So in both of these two cases, 1 upon a is coming outside. So accordingly, what we have is like this y of e to the power j omega can be represented as 1 upon mod a integration over minus to plus infinity, because as you know, this is basically uh, a definite integral. So over here, if we make it like minus to plus infinity, then one minus sign will come outside. So minus 1 upon a integration over minus to plus infinity. And if a is negative, that is basically 1 upon a will be the positive number. So ultimately, we can write it like 1 upon mod a integration over minus to plus infinity x of tau e to the power minus j omega by a tau d tau. So if the signal is scaled in the time domain, then the Fourier representation is represented like 1 upon mod a. So there is a change in the spectrum by some amount, 1 upon mod a multiplied with x of e to the power j omega by a. That means the corresponding frequency components are also getting modified. The frequency components are also getting modified. If a is greater than 1, in that case, in the compressed case, what we find, if the signal is compressed in the time domain, that means it will be expanded. It will be expanded in the frequency domain, and vice versa. If the signal is expanded in the time domain, that means if a is less than 1, signal is expanded in the time domain, then it will be compressed in the frequency domain. So that is the scaling property, and ultimately we come to the final relationship, which is the Parseval relationship, which says that the signal representation in the time domain and the frequency domain are two different approaches of observing the signal or visualizing the signal. Eventually, we know that the signal energy Ex can be represented as integration over minus to plus infinity mod xt squared dt, but in general we are assuming the signal x of t is a complex signal. So in general it's a complex, so we can represent like we can represent it like simply x of is whole square dt, x of x square t dt. But in case it's not a real signal, if it is a if it also contains some imaginary components, in that case we can represent like mod xt. Otherwise we cannot take into account the negative value over there. Right, so this mod xt square is nothing but xt multiplied with x star t. So we know that what is x of t. So this x of t, we know that from the inverse Fourier transformation, this x of t is given by 1 upon 2 pi integration of minus to plus infinity x e to the power j omega e to the power j omega t d omega. So from that, what is x star t? If we just take the complex conjugate of this equation both sides, then x star t is equal to 1 upon 2 pi integration of minus to plus infinity x star e to the power j omega e to the power minus j omega t d omega. Then what we get, e of x is equal to integration of minus to plus infinity mod xt square is basically xt multiplied with x star t. If xt is real, then xt and x star t will be same. If xt is not real, if it contains some imaginary component as well, in that case it will be xt multiplied with x star t. So already we have got xt, and we are multiplying this with x star t. X star t has been evaluated from this expression, so 1 upon 2 pi. We just substitute this value over there, and if we change the order of integration, then this x star e to the power j omega is over there, and then we have integration of minus to plus infinity xt e to the power minus j omega t dt, and then finally we have the double integration. Over here we have d omega. So this particular thing xt to the power minus j omega t dt is basically the Fourier transformation of the signal x to the power j omega. So what we have is 1 upon 2 pi integration of minus to plus infinity x to the power j omega multiplied with this one, that is x to the power j omega, and x to the power j omega multiplied with x to the power j omega will give us mod x to the power j omega whole square t omega. So we started with ex is equal to minus to plus infinity mod xt square dt, and ultimately we have arrived at ex is equal to 1 upon 2 pi integration over minus to plus infinity mod x to the power j omega square d omega. So if we know the xt in the time domain, or if you know the xt, the representation of xt or the manifestation of xt in the frequency domain, that means x to the power j omega, then also we'll be able to find out its frequency component, and from this frequency component we'll be able to find out its energy. And so it is possible, very much possible, and these two are same basically. So minus to plus infinity mod xt square dt, that is energy representation by considering the signal in the time domain, and minus to plus infinity mod x to the power j omega square d omega. So there's some square term will be there. That is the manifestation of the signal energy in the frequency domain. So if we calculate, if you know the Fourier transformation of the signal x of t, then also we'll be able to find out its energy. It doesn't involve the signal to be in the time domain. So we can take it in the time domain, also in the frequency domain, to find out its energy. And this particular relationship is known as the Parseval relationship. So today we have discussed some of the important properties of Fourier transformations that will help us in calculating the Fourier transformations of some signals which are derived from the actual signals. Suppose we know some of the signals, say for example, we know the signal, say we know the Fourier transformation of simple rectangular pulse, right? Now, if you're asked to find out the Fourier transformation of ramp signals, which is basically the integrated version of the signals, so you'll be able to find out it very easily using these properties. So with this, let us conclude the session on Fourier transformation.